Okay, in 14.3, number 36, and it's a double integral in polar coordinates, I believe. The directions say, use a double integral in polar coordinates. So, if you read the directions, it helps. And to find the volume of this solid, and then they give me this description. Z equals, right off the bat, this is a little weird. Maybe I'm going to regret picking this problem. This is the natural log of x squared plus y squared. They also give me z equals 0. And then they also give me some other boundaries here. X squared plus y squared is greater than or equal to 1. X squared plus y squared is less than or equal to 4. That's interesting. X squared plus y squared is greater than or equal to 1. X squared plus y squared is less than or equal to 4. So it has been a long weekend, but if I want to find the volume of this solid, I don't necessarily have to sketch. There's a 3D solid here, and I really don't know how to sketch that. I don't. But I'm going to assume it lives up over the XY plane, and I'm going to sort of assume that what they've given me here is sort of a top and a bottom, or a ceiling and a floor, so to speak. And so I think when you set up a double integral to find volume, what goes in here, do you remember? The ceiling, or the surface, or so I think I'm going to be integrating this thing, log of x squared plus y squared. So that wasn't much of a decision. Look, who are you integrating, you know? So there you are. That's the only surface they gave you. But you are between the floor, the good old z equals 0. I'm glad they gave me that. Otherwise, I'd have this infinite, I'd have no floor. Okay, so I got a floor, I got a roof or a ceiling. I'm going to integrate that ceiling over a region that lives in the floor. Now, to me, there's a region over which I'm integrating. And there it is. That's described very well right there. And I don't know how quick you read and see. I read and see this pretty quickly. I want to draw a picture of this region. This is the region over which I'm integrating. Do you know what this is? A circle. Circle, radius 1. But then the funny thing is they said greater than or equal to. But it is a circle of radius 1. Greater than or equal to might be on the outside of it. And then they've got this, which is a circle of radius 2. And, sorry about my circle. A circle of radius 2, and it says less than or equal to it. So I think I've got this figured out. I think it's between these two. This is the region in the XY plane. Again, the z-axis is coming out at you, and there is a surface. We're integrating a surface over this region, and that's the region that was described. And when we integrate over circular regions, we learn that polar coordinates is a nice, we should work in polar coordinates. In polar coordinates, can you tell me the name of this outer circle? R equals 2. That's his name in polar coordinates. Can you tell me the name of the inner circle here? R equals 1 is the name of that inner circle. In polar coordinates, that's the beauty of polar coordinates. And so I think I want to, so I started to set up this integral, and I put this function in here, but now I'm thinking about polar coordinates, so I'm going to change this. Okay, here I go. First of all, I'm going to change the function. I'm going to switch it into polar coordinates. And when you see an x squared plus a y squared in polar coordinates, x squared plus y squared is r squared. So I just changed this surface, z equals that, into polar coordinates. Z equals the ln of r squared. You know, I was going to debate out here whether I should put dy dx or dx dy, except now I know I'm in polar coordinates, so I should put r dr d theta. Don't forget the extra little r that comes with that. That is the dA The dA is that. It has that extra little r that comes with it. Okay. Oh, okay. Now I'm integrating over this region in the xy plane or in the polar plane. I want to integrate with polar coordinates, and so I need bounds for r. My inner integral is bounds for r. My inner integral is bounds for r. R moves from the pole out, and what would you say bounds for r would be?
1 to 2.
1 to 2. Yep. Yep. You don't want 0 to 1. You want 1 to 2. So you integrate from 1 to 2. And theta?
0 to 2 pi.
Theta goes all the way around at 0 to 2 pi. And that's awesome. And you've set up this integral to find the volume of some solid. I don't have the picture of the solid here. There is a solid here. This function lives over this region somehow. But anyway, the volume of this solid will be this double integral. You know, now it's a matter of cranking through this double integral, which, that's a challenge. I mean, we always have two challenges. Drawing, setting up the integral, and then doing the integral. To save time on quizzes and tests, there will be some setup questions only. You know, good old setup, and don't bother to even get the answer. But there will be some you have to get the answer, of course. Yeah, this one's a little weird. The integrating log is
1/2 du equals r dr.
yeah, that log. Yeah, log is kind of a funny thing to integrate. Anyway, I think I remember the only way to integrate natural log is to involve integration by parts. And not really the tabular method, but integration by parts. So I'm going to try that. So I'm working on this inner integral, and I'm going to try to do integration by parts. What am I going to do? I think I'm going to call u something, and I'm going to call dv something. And it's kind of counterintuitive. It's old integration by parts. I'm going to let u be the log of r squared. Hey, if you let u be the log of r squared, then you need du, you guys. This is how this game works. You need du. Do you know what du would be? The derivative?
2 over.
Yeah, let's see. 1 over r squared times the chain rule, 2r. If he cleans that up a little bit, he said 2 over r, dr. Yep. That's du. What's dv? I think I'm going to call dv that little r, dr. And how do you get v? Do you remember how to get from dv to v? You actually integrate, which is kind of counterintuitive. See, look what I'm doing. I'm growing this r, which is not usually the case with integration by parts, but involving logs it is. Involving logs, it's sort of the backwards little game you play. This is going to work out beautiful now. When you do integration by parts, what's funny about it is, so keep in mind, I'm doing this inner integral is what I'm doing. And this inner integral is, according to the integration by parts rule, here we go, the answer is uv. UV, 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 there it is, UV, UV, you guys okay with that? UV minus the integral of v du, v du, v du, v du. Oh, here's my du and my v. My v du is so sweet. The 1/2 and the 2 cancel. The r squared over r cancels. I end up with an r dr. Doing integration by parts, where after you set up the u and dv, the answer to the integration by parts is uv minus the integral of v du. So when you do integration by parts, what always kind of sucks is you got another damn integral to do here, but it's not too hard. What is this little integral? This little integral is r squared over 2. R squared over 2. Cool. finished, fini, as they say. Fini. We're finished with the inner integral. And now it needs to be evaluated with the bounds 1 to 2. The inner integral is finished. It kind of took a little work, took a little integration by parts, but the inner integral is finished. I'll evaluate it with these bounds. This will be easy, you guys. In the end, I think this will be a number. Let's do it. I'm plugging in a 2. When I plug in a 2, I get 4 over 2. I get a 2. 2 ln of 4 minus, when I plug in a 2, that's a 2. Minus, when I plug in a 1, the ln of 1 is 0. But I do get this negative 1/2 right here. So there's my answer. That's a 2 log 4 minus 3/2. Because that's a negative 2 plus a half. Negative 3/2. That's it. That's the answer to the inner integral. I'd like you to notice something. It's a number. It is a number. There's no variables in it. Can you integrate it with respect to theta from 0 to 2 pi? Can you integrate it with respect to theta from 0 to 2 pi? How do you do that?
2 ln 4 theta minus 3 over 2 theta.
Thank you. You slap a theta on it, right? It's a big old constant times theta, and then you're gonna. What are you gonna plug in for theta?
2 pi.
2 pi. I mean, it's over, right? You see the end? It's over. I could cut the movie off now, and you see the end. The end is when you integrate a number with respect to theta, it's all this times theta, evaluated from 0 to 2 pi. You plug in your 2 pi, and the problem's over. I'm going to move way over here and tell you that the answer is 2 ln 4 minus 3/2 parentheses times 2 pi. Whatever that is, it's the volume of this solid blah, 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 blah from problem 36. That's pretty cool. Did run into some nasty little integration by parts. It wasn't really nasty. It was kind of easy. Integration by parts there. That was a good polar coordinate problem, I guess. I really like these problems in the 30s. You guys should work on these. 14.3 in the 30s and 50s there. Some good stuff. You know, let's have this discussion quick. You know, when we're integrating over a region in the XY plane, you know, then what we were doing sometimes is we were kind of dicing it up into little dx and dy. That's the and this is this little chunk of area, and we call that little chunk of area dA. But you know, using a little geometry, I guess the dA is dy dx or dx dy. You can sort of see it. But when you're in polar coordinates, our little chunk of area doesn't look like that. I mean, because we don't, you know, this is in rectangular coordinates. We move horizontal and we move vertical, and we create this kind of grid system, horizontal and vertical grid system like that. Well, in polar coordinates, it looks like this. You kind of, well, your region can look like that, but what you're doing now is you're emanating from the pole, you're emanating and you create, this is your shape. And what it is it's estimated to be a sector of a circle. A sector of a circle. Actually, if it was all the way down to here, bless you, that would be a sector. That's called a sector of a circle, if this is a circle. And for very small little changes in theta, we can call that a circle. What I'm trying to do here is I'm trying to explain. How do we get that r d theta? This dA is r dr d theta. Now I don't know, can I think this through a little bit? It's from this geometry. It is, let's see, the first thing I need to know is the area of a rectangle, length times width, okay? The area of a sector of a circle, I guess that's new. It's 1/2 r squared theta. That's true. That's probably not on the tip of your brain anywhere, but it is true. This is a formula for the area of a sector of a circle. Hang on. Terrible picture. That means from the center, this is called a sector of a circle. And so you need to know the radius, r, and you need to know the included angle, theta. Watch what happens what if you wanted to do the whole circle? What do you think your theta would be for a whole circle? 2 pi. And then the sector of your circle would actually be the whole damn circle. But your theta would be 2 pi. Watch what happens if you plug a 2 pi in there. If you plug a 2 pi in this formula, it becomes pi r squared, the area of a circle. But it also works for any sector of a circle with this included angle and this r. So that's what we're doing. We're calculating areas of a sector of a circle. So hang on. My theta is a very small little slice of theta. What's it called? D theta. Oh boy. I was going to say one of these R's, I kind of got an R1, I kind of got an inner radius and an outer radius, don't I? I kind of got an R1 and an R2. What if I just average those? R1 plus R2 over 2. I could go. I might call that this R. And then I got this little thing, this little change in R, which I would call dr. Boy, that was that's my explanation. Can I say it better? Maybe I could. What am I doing? I'm taking this formula, I'm making this 1/2 and R, 1/2 R times another R times a theta. Times a theta. My theta turns into the d theta. One of these R's turns into one of these R's, and the half of an R turns into this, which is this. Well, you guys were happy when I just said, just memorize the r dr d theta.
Yeah.
But there's sort of an explanation here. The key is, you're not doing this picture, you're doing this picture. You're working differently. You're working with this change in R, estimating a sector of a circle. That's what this little sector is. Or actually the difference between two sectors of a circle. Yeah, that's what it is. Yeah, I'm sorry. It's 1/2 R2 squared theta minus 1/2 R1 squared theta, isn't it? Is that what that is?
Yeah.
That's what this picture is? Yeah, let's play with that a second. What if you factor out the theta, then you have, and the 1/2, then you have R2 squared minus R1 squared, which I could write as R2 minus R1 and R2 plus R1, couldn't I? You guys see that? Ah, dude, now we got it. That R2 minus R1 is the dr. That theta is the d theta, and this other guy, this R1 plus R2 divided by 2 is sort of my R. my average R.
Well.
Yeah, that's better. I mean, I was trying to just analyze this, but that was good. I should have subtracted these two R1s and R2s. Anyway, that's a good, anyway, enough of that. Polar coordinates, you need your R, D, R, D, theta. Of course. Okay, listen, I want to move on. I want to move on to something else. And, I mean, a lot of good problems we could do. I'd like you to do them. You need to do them more than me. So you should work on some of these good problems in the 30s there. If I go to 14.4 and 14.5, all of a sudden what happens is I'm using more double integrals, but now I'm using them for a purpose. And in 14.4, you know, I mean, it's just more double integrals. And I got myself a nice sheet of notes here, and it's full, front and back, nice sheet of notes. And I might share them with you. Oh my goodness. Yeah. In 14.4, I can use these double integrals to find center of mass. Now, that makes me, did you guys do that in Cal 2? In Cal 2, you might have done some center of mass. A little bit. But you always had a constant density. See, now I can do the center of mass of some kind of shape, and I can have, we always had a constant density. What does that mean? It was all the same material. Like if it was all tin, it's one density. If it's all gold, it's one density. If I have a variable density, Jesus, it could be silver mixed with gold, mixed with wood, mixed with paper, mixed with air. I mean, I can have a variable density object here, and then I can try to find the center of mass, and I can use a double integral to do it. Right, I'm not going to write all these on the board. They're in your book. Oh my God. Then I can find moments of inertia. After I find centers of mass, I can find moments of inertia. So I can do all this with double integrals. In 14.5, I can do something else. I can do surface area. Now, what have I done so far? What have I done before I did all this? What was I doing in 14.1, 14.2, and 14.3? What was I using double integrals for? Do you recall?
Volumes.
Yeah, something sort of tricked me and said I was doing area in 14.1. Remember, that was sort of a lie. And then the rest of the time I was doing volume. And I opened today doing a volume problem. So I was using double integrals to find volume. But with a slight variation, I mean, if your double integral is integrating a density function, then maybe you're finding center of mass or the moment of inertia, so double integrals are definitely more than just area and volume. They're all these topics. This surface area is kind of a trippy one. It's a double integral over a region, and it is, you get to integrate this. 1 plus the partial derivative of f with respect to x squared plus the partial derivative with respect to y squared. That's the surface area. I'm going to give you these formulas. You don't have to memorize a bunch of formulas. I'm going to give you this nice little sheet. Let's actually try a surface area problem. I'm going to go to 14.5 and just try to read one from the book. Let's see what happens. In 14.5, if I want to do a surface area problem, how terrible will this be? Okay, I want to do this one, number 12. So number 12 is a surface area problem. And here's what they give me. They give me a function. Okay. They give me a function. They give me number 12 in 14.5. They give me a region. The region is described like this. They're very careful to describe their region as a set. It's the set of points x, y such that x squared plus y squared is less than or equal to 16. I think you might, I mean, that's how they describe their set. Okay, again, I'm not finding volume. If I was finding volume, I hope you know how to set up the integral. We've been practicing that. But I'm not finding volume, I'm finding surface area. So that means I got to set up this integral. Okay, that means I need a couple partial derivatives. I need the partial derivative with respect to x.
Why?
Yeah, the partial derivative with respect to x is y. The partial derivative with respect to y is x. That's not confusing. And then I would work on setting up this double integral. Okay, here I go. I think I'll have a square root of 1 plus that y squared, and then that partial derivative with respect to y, which is x squared. I'm going to work on my bounds. Maybe I need dy dx, maybe I need dx dy. I don't know. Let's see. I mean, here I am setting up the integral, using these partial derivatives to help set up the integral from the surface that's given. But to come up with the bounds, I hope you realize it's a whole new game. To come up with the bounds, I got to focus on the region over which I'm integrating, which has nothing to do with him. The region over which I'm integrating is described here, and you can draw that or see that, I hope. What is that? Good. Circle of radius for the interior. Yes, yeah. I'm integrating over this circle of radius 4.
So we can do either x or y.
So I could do x's or y's, or
Polar
I
coordinates.
should do polar coordinates. I mean, I don't know how long it's going to take me to realize that. I mean, I got this thing partially set up here. I was sitting here debating, maybe I should do dy dx, maybe I should do dx dy, but really, as soon as I draw that picture, another thing that helps is when I see this x squared and y squared, that makes me kind of want to convert to polar. But really, the region over which I'm integrating is what makes me want to convert to polar. So it's a circular region, dude, I want to convert to polar. So I started setting up this integral. I'm going to abandon it and convert it to polar, all right? Okay, here we go then. I'm going to set up an integral. So the integrand now becomes the square root of 1 plus r squared, the x squared plus y squared, which came from these partial derivatives. I mean, you had to kind of do what we did. You had to work in rectangular coordinates to get this baby set up. Once it's set up, you can switch to polar. And the dA is going to turn into r dr d theta. And the bounds. And the bounds are all about the region over which I'm integrating. And I sketched a little picture of the region over which I'm integrating.
4, 0 to 2 pi.
0 to 4 for r. 0 to 2 pi for theta. And this was a surface area problem. So I used this formula from 14.5 for surface area. Hey, just for fun, what if I'm doing this 12 in 14.5, which was a surface area problem, but what if you wanted to find the volume? How would this problem differ? Well, you don't do this for volume. This is what you do this for surface area. For volume, what do you integrate? The actual ceiling, the function. Thank you. The actual function that's there, which is x times y. Hey, again, you're integrating over this region, so maybe you want to switch to polar. How do you take that xy and switch it to polar? An x is r cos theta, and a y is r sine theta. Those are true facts that we should know. An x is r cos theta, a y is r sine theta. I'm about to put my r d theta here. I mean, I'm integrating the surface, switch to polar. Again, 0 to 4, 0 to 2 pi, I believe would do it. Yes, sir.
That's our ceiling. What's our floor then?
Well, what is our floor? I'm assuming, I didn't write the floor, but I was always assuming our floor is the floor. The xy plane z equals 0. A lot of times, when you're actually finding volume, I adapted this problem. Okay. When you're actually finding volume, somebody should tell you the solid that you're finding the volume of is a solid. And it needs to have boundaries on the left and the right and the sides and the bottom and the top. And so they should tell you z equals 0 is part of your boundary. You know, originally this problem started as a surface area problem. You know, what it was is, I'll just show you. I do not know what that is, but it's some kind of surface, infinite surface. But I am finding the surface area of it. Am I finding the infinite surface area of it? No. I'm finding the surface area of it only over the region in the xy plane described like this. So I'm finding maybe, look, if you go up, I'm sort of finding that surface area of this thing over that region when I do this problem. But then just for contrast, I wanted to, let's go back and set up a volume problem, which means I'm finding the volume of this. Now I'm finding the volume of that whole thing, which is different problem. Different problem. Similar balance, similar region, different integration. Yep. I don't know why I did that. I just wanted to leap back to do that. Again, a lot of these I like to help you set them up, and I feel like maybe you can do them. This is kind of a good one. Back to this one and abandon that one. How would you do this one?
U substitution.
Yeah, it's a nice U substitution. Thanks for that R there. You can do a U substitution. Du will kill that R. Maybe spits out a half, and you got the square root of U, and right, you can integrate this now. How would you integrate this one? Really what you do is you'd avoid, again, the first integral. See, this first integral is with respect to r. So I don't know, but you had to work with r's, and you said, let's do U substitution. U equals 1 plus r squared. Du is 2r dr. That's going to take care of that. Watch out for, you know. But anyway, back to this one. If so for the first integral, you treat the cos theta and the sine theta like they're constants. And for the first integral, you're integrating with respect to r, and you actually have an r cubed. So you actually have this.
That's a constant.
And then you're going to integrate this. And so with respect to r, you integrate the r cubed, and you get 1/4 r to the 4th. These guys just sit here as constants. You evaluate from 0 to 4. You guys with me? Mm-hmm. When you plug in your 4, it's kind of sweet because it cancels with one of these 4s, leaves me with 64, I think. So I'm left with 64 cos theta, sine theta, d theta, integrated from 0 to 2 pi. Yeah. Let's just finish this. How would you finish this one? U equals what?
Sine.
I would do sine. U equals sine because then du is cosine. So what just happened? This du is taken care of there. This is this. So I end up with 64u du. All right. How do you integrate a u? Du. U squared over 2. 32u squared. 32u squared U is the sine function. And do this from 0 to 2 pi. This is the funny part. Plug in a 2 pi and you get 0. Plug in a 0 and you get 0. Damn it. How much volume did we just get? 0. Does that make any damn sense? 0 volume?
Not according to that picture.
Yeah, good. Not according to the terrible picture. Yep, it is a terrible picture. I should have realized a few things. One thing I should have realized is I'm graphing this XY. I'm working over this entire region. You know, when you're in quadrant 1, those guys are positive and you're positive. Your Z is positive. When you're in quadrant 3, those guys are negative, but that makes your Z positive. You guys following me? If you're in quadrant 1 or 2, if you're moving around this XY plane and you're in quadrants, 2 or 4, that value is negative. So my surface, Z, is above and below this in a very symmetrical fashion, such that when you integrate over this to find the volume, you get a net volume of 0. The double integral, when you just kind of blindly set this up and do it, it treats volume above the floor as positive volume and volume below the floor as negative volume, and it just added it all up and we got 0 volume. So that's the explanation, which means this was not the picture. Right, the picture was slashing through the origin, kind of. Some of it is above, some of it's below the XY plane. We got a net volume of 0. By the way, that won't happen with surface area, will it?
There's no negative.
Surface, there wouldn't. Yes, yeah, there shouldn't be negative volume, but surface area should work. The surface area is the surface area, whether it's above or below. It should still be the surface area. By the way, the thing you're integrating is a positive square root. You're integrating this positive square root, so you're not integrating anything below the thing you're integrating. Is a positive quantity. Huh, that's cool. All right, you guys. All right. I want to move to these triple integrals, really. That's what I'm trying to do. So let's do that. I'm moving to 14.6, triple integrals. All right, hang on, you guys. Now, let me just help you here. Let's think this through a second. Now, if I had a double integral over the region R, dA. Now, what did we call that?
Volume.
Well,
Area.
All right. I know it's weird, but we did call it area, but we kind of learned that it's really
Volume.
it's volume of something with a height of 1. And the book made us call that area, and we could see why that's area. It's numerically equivalent to the area. The volume of something with a height of 1 is equivalent to the area of its base. So that's okay. We'll let them slide. But it really was volume. And then what we said was when we put a function in there, when we put a function in there, now that's my ceiling and my floor. I'm integrating a double integral under a function over the region R in the XY plane, and this was volume. Is that okay?
Mm-hmm.
All right. So now we move to triple integrals. So triple integrals. A triple integral integrated over a solid Q. I can't use a region. This is not a flat region R. See, it's a triple integral. It's over a solid Q. And it's not dA. It's going to be dV. By the way, guess what the dV could be?
dx, dy, dz.
dx, dy, dz. Well, hang on.
dr, R.
Yeah. All right, hang on. We'll get back to that. But a triple integral with a dv there, with no function there, right? With just a 1 dv, what do you think that is?
Volume.
That's volume. Is that okay? We'll call that volume. Just like we called this area. I guess it was kind of a lie, but
Because dA is x1, and then dv is x, y, z, 2. Length times width times height.
Oh, without a function.
So that's kind of the
Okay, I missed that part. Okay.
so yeah, without a function, this was the area of the region R. Without a function, this is the volume of the solid cube.
It's past volume. 4D.
Right, that's what I was going to
Is that
say.
right?
Here comes the next one. So what if there's a function here? Look, now there's a 4-dimensional function sitting here. This is W equals function of x, y, and z. You're integrating a 4-dimensional function over a 3-dimensional solid cube.
What does that give us?
That, there's my answer.
But we still.
I think I need to know why we need these.
Yeah, we're trying to find something we don't know what it's for.
Forgive me the answer.
All right, hold on. Because, remember, now we just barely did it, but when I hand you your little, anyway, we did move into 14.4 and 14.5. And sort of, we just did it in 10, 15 minutes, so real quick. But what we learned there in 14.4 and 14.5 is that double integrals can be used for moments of inertia. Depending on what you integrate, it's not always just area and volume, okay? A double integral is not just area and volume. If this is what you're integrating, a double integral is surface area. You know, and if you put a density function in there, then you're finding the moment of inertia or the center of mass, so these things can be constructed. These can be constructed to mean something other than area and volume. I like area and volume. It's something I really can grab a hold of. These other things are a little more abstract. Moments of inertia and center, you know, they're a little tougher. But
so they're formulas for
so
integrals.
So right, if this is density, then this is probably some kind of center of mass or moment of inertia, right? But in terms of our area, volume, what's the next level thing? There is no geometrical definition for this. And using my definition of geometry as being area, volume, or what, some 4-dimensional volume, right, doesn't make any damn sense. But it could be something. It could be surface area, or it could be,
Calculating a topography.
it could be some moments of inertia. There's some stuff. Read the damn book. But we're in 14.6. So now we're in 14.6. And we're doing triple integrals. But if someone says, do a triple integral to find the volume, if someone says, do a triple integral to find
You
volume,
don't need a function.
then what are you going to put in here?
0.
Thank you, a 1. Right.
Yeah.
And you're going to set up your dv and to find the volume. And to set up your dv, what could it be?
dx, dy,
dx, dy, dz. What else?
dx, dz.
dx, dz, dy. What else?
No.
dy, dx, dz. What else? dy, dz, dx. What else?
Oh, man.
dz, dy, dx. What else?
dz, dx, dz.
dz, dx, dy. Right. This is what sucks too about triple integrals. When someone says set up the dv, you got 6 choices. And you can do, you know, we had dx, dy or dy, dx. We had 2 choices. Now we got 6 choices. And if someone says, try to set this up in all 6 orders of integration, that's kind of a challenge to set it up in all 6 orders of integration. There is a problem or 2 like that. I wouldn't do 12 of those problems.
One of them normally 0 to 0.
Well, you got to let somebody go first, and then you got to think through the 3-dimensional figure. And it was always easy doing these double integrals because we can always just worry about the two-dimensional region. Now we got to sketch the three-dimensional solid Q to see how to set up these bounds. And we got a lot of options with these bounds. Let's try one. Let's try one. I'm going to 14.6 and I want to try a homework problem. Hey, after this I can do 14.7. This is awesome. Yeah, they got some center of mass and moment of inertia formulas in 14.6. They do. They do. No. All right, I'm gonna try this. 16. I'm in 14.6. Great problem number 16. It says, find the volume of the solid, or it says set up a triple integral for the volume of the solid, and it says the solid is bounded above by the cylinder z equals 4 minus x squared. Let me write this down. It said, that was nice of them to say that, bounded above. That's very nice. By z equals 4 minus x squared. The solid that we're describing is bounded above by that, and it said bounded below by z equals x squared plus 3y squared. The paraboloid, they called it a paraboloid. X squared plus 3y squared. Well, you guys, even though I kind of went off over here and I said, look you guys, this dV sucks, man. Look, you can do all these different orders, 6 different orders of integration. The way we really like to think is we kind of like to take care of z first. You know, z is our top and bottom, so we like to do z first, and then we do the dy dx or the dx dy. So this is our favorite one. And that's how and this is how they presented this to me. So I'm gonna set up a triple integral. And I think I'm going to do dz, dy, dx. I'm not sure. dz, dx, dy. I'm not real sure about about this order. But I want to do z first. And who's my lower z and who's my upper z? Duh. I mean, it's bounded. Whatever this solid is, I can't draw it too well. I could try. But it's bounded below. The lower surface is him. And so I think my bounds for z are this z to that z. Lower z to upper z. Are you okay with that? Yeah. So here, how do I write that? This is my lower z to my upper z. You know, these bounds for z, these are z. This is z equals him and z equals him. It's like a z1 and a z2. And my bounds for z are from that z to that z. And it's typical, man, that your bounds for z are in terms of x's and y's. You got a function of x's and y's, and then you got another function of x's and y's, although there's no y's there. Hey, to finish this problem, I mean, anyway, I really needed a three-dimensional picture to see who was on top and who was on bottom. I didn't really need a three-dimensional picture, though, because they told me who was on top and who was on bottom. Otherwise, I would have needed a picture to try to see who's on top and who's on bottom. But they were nice, and they told me that. To figure out the bounds for y and x, it's no longer really a 3D problem. I need to look at the 2D cross-section of this, or the 2D region over which I'm integrating to finish the bounds for this problem. That's a little bit tricky. That's tricky. Let me think about this here. You know, when they wrote this, they referred to it, and I should know it anyway, but they referred to it as a paraboloid. It is a paraboloid. It sits at the origin, and it opens kind of up and out. It's kind of an elliptic paraboloid. So there's the bottom. That's the bottom. The top is this thing. What the hell is that thing? They called it a cylinder. When they say cylinder, you remember we had this category of cylindrical surfaces. They weren't all cylinders. They were cylindrical surfaces if they had a missing variable.
They were parallel to the axis.
And they would be parallel to that axis. See, I know what that is. That's a That's hitting there at 4, and it's hitting the x at 2, and hitting the negative x at negative 2. It's a parabola, but it's running infinitely in the y direction. Here it is. You guys follow this?
Yeah.
So now everything's obvious, I hope. Oh, God.
Hold on a second. Hold on. Don't abandon ship yet. Hold on. So there's a funny parabolic bottom, and then this thing comes slicing down here. It's going to hit. It's sort of going to hit this bottom. You know, maybe it's kind of like this. This is my top. I don't know how it looks on the corners. It might get kind of funny on the corners. It might kind of rise up a little. There's a top and a bottom. We already got that all figured out. We got our top and bottom figured out. I'm trying to figure out this region over which I'm integrating, which I want to speculate is sort of where they intersect. I think I need that. See, actually, you know, if I say, look at the region in the xy plane, look at the region in the xy plane over which you're integrating. Well, there ain't no region in the x. There's a damn dot in the xy plane. You know what I mean? So the region over which I'm integrating is the broad, wide place of this solid, which is where they intersect. And it's that shadow in the xy plane that I'm really kind of looking at. So I need to focus on this intersection region. This region of intersection, you could call it. How would you do that, you guys?
Send a z equal to each other.
Probably set this z equal to that z, exactly. Wonder what happens. Wonder what happens if I set that z equal to that z. That 4 minus x squared should equal that other guy. Huh. I'm going to add this over there. I'm going to get 2x squared plus 3y squared equals 4. That's the region of intersection. That is it. And I don't know if you know what that is. Do you know what that is? You should know what that is. What'd you say? It's an ellipse. I mean, if they were the same coefficient, it would be a circle. With different coefficients, it's an ellipse. And it's kind of what my picture shows. See my picture? You guys laugh at my picture one more time. Yeah, I've got this elliptical region over which I'm integrating, I guess. And I don't need to go draw it. Now that I know it, what am I trying to do? Oh, can I come up with some bounds for y? Well, I think I should solve for y, which would be 4 minus 2x squared over 3 square rooted plus or minus. Is that y? I think that's y, right, you guys? What do I do? Subtract that, divide by 3, square rooted. And so I think my bounds for y are the lower y, which would be the negative square root of 4 minus 2x squared over 3, to the upper y, positive 4 minus 2x squared over 3. By the way, notice, these bounds for y are in terms of x. I mean, this is how these things work. The bounds for z are in terms of the remaining variables, x's and y's. Once you're done with z, the bounds for y are in terms of the remaining variables, x. The very last bounds are going to be numbers, which means, what the hell are those numbers going to be? This is an ellipse.
2 to negative 2? Or negative 2?
I don't know. Maybe can I, if I want to know that my extreme x's, maybe I should let y be 0. If I let y be 0, I get this, which means if I divide by 2, I'm getting square root of 2 and negative square root of 2. I'm going to say that's it.
That's what I said.
Yeah, too close.
You're close.
Dude, and then who wants to do this integral?
No.
I don't know, you can do the first part real easy. How do you integrate with respect to z? You put a z,
Yeah.
and you evaluate from here to here. Right, you guys? I mean, right? That's the first part. That's nothing. So you get 4 minus x squared minus 3y squared. It's this guy minus that guy. That's actually 4 minus 2x squared minus 3y squared. So now I'm integrating this with respect to y. Hey, even that's not too hard, is it? But then you got to plug in these shitty bounds.
Yeah.
And so I don't really want to do this. The problem said, set up the integral only. It did. So we could stop right here. So, triple integrals. Good luck. Listen, this chapter concludes. I want to show you. I got 10 minutes. I'm going to tell you something here important. This chapter concludes in 14.7, which is triple integrals in new coordinate systems. So I'm not going to 14.7 quite yet. I'm really not going there yet. But I'm just telling you, this chapter concludes with section 14.7, which is triple integrals in other coordinate systems. So here I am today in 14.6. I'm doing a triple integral in the rectangular coordinate system, meaning x's, y's, and z's. Okay, there are other three-dimensional coordinate systems. One of them, and this is kind of back in 11.7 when we introduced these other coordinate systems. So we got good old x's, y's, and z's, and we call that the rectangular coordinate system. Okay, here's another coordinate system. It's called the cylindrical coordinate system. Now check this out. Check this out. It's a new coordinate system, but all it is this: r and theta and z. Now, if you just saw that and didn't know it was called cylindrical coordinates, what would you call it?
So
You might call it
polar.
You might call it polar. Thank you. It's just polar. I mean, if you notice what happened here, the x's and y's got turned into r's and thetas. And the z is still the same old z. I mean, see, here's the funny thing. In two dimensions, we have XY coordinate system called rectangular coordinates, and we have the R theta coordinate system called polar coordinates. Now, you sort of learned about him in Cal 2, but we definitely reminded ourselves about him now in chapter 14. But this is a two-dimensional coordinate system, and he converts to him through this picture. We had this great picture. There's y, there's x, there's theta, there's r, and you know, so this picture helps you convert back and forth and helps you understand converting from rectangular to polar, rectangular to polar. Okay, well now look, add a z to that and you're in 3 dimensions. Add a z to that and you're in 3 dimensions. But his name now becomes cylindrical coordinates. It's kind of weird. I don't know, the name is kind of weird to me. I like to call it 3D polar is kind of what I like to say. It's just polar with a z attached. It's just, because I just want you to understand, the word polar is two-dimensional. It gets you around, it's another way of getting around the XY plane. Polar doesn't necessarily come with a z attached. Polar is two-dimensional. You can get around the XY plane using polar coordinates. Two-dimensional, two-dimensional. But move around the XY plane in polar coordinates and then rise up a certain amount of Z, you got 3D polar coordinates, I guess. You got R, thetas, and Z's, which we call cylindrical coordinates, or 3D polar. Check this one out. This is the brand spanking new one for you. It's rho, theta, and phi. And it's spherical coordinates. And this is really brand new. And this is a 3D coordinate system that's brand new. It's introduced to you in 11.7. I'm introducing it to you now. Because what happens is when I go to 14.7, I got to do triple integrals in cylindrical coordinates, and I got to do triple integrals in spherical coordinates. You hear me? I got to do the last section. I got to do triple integrals in these new coordinate systems. This one's not that new. It's just polar with a Z attached. This is brand new. This is brand new. Let me just tell you what it is. Here it is. If you want to get to this point in space, one way to get there is rotate an angle theta, walk out this distance r, but it's not called r, it's called rho. Well, wait a minute, so how far did I rotate? I rotated over here to the shadow of rho. This is the shadow of rho. Right, hold on a second. You can go over here x, you can go over here y, and you can go up z, and you can get to this point. Right? X, y, z. But you can also rotate theta. Oh, you can rotate theta. Watch this. You can rotate theta, walk out r, and go up z. That's this, r, theta, and z. There's your r. That's your good old r in the xy plane. That picture right there in the xy plane is this picture in the xy plane. Right? Okay, so what the hell am I saying? Rotate theta, walk out r, and go up z. Well, anyway, okay, but what I'm really trying to do now is the spherical coordinates, which is go out, this rho is kind of like a 3D version of r, as you can tell. It sticks out from the pole, it's rotated over a certain angle theta, and it's rotated down from the z-axis a certain angle phi. That'll get you to this point. It's rho, theta, phi. And don't get theta and phi confused. They're both angles. But theta is measured like theta always is measured, and phi is measured from the z-axis down. I mean, let me just see something. Hang on. If I wanted to hit this rag with spherical coordinates, what would I do? If I want to hit the rag with spherical coordinates, I need a rho that goes from that origin to that rag. I need it rotated a certain theta from the positive x-axis. So I got to rotate a certain theta, get a stick that's that long. Oh, and I got to rotate that stick down from the z-axis a certain amount of phi. And then it'll hit the right spot. Bam. This is 11.7, and in 11.7 they introduced these ideas. They got all these pictures, they got all these equations that relate how to convert from spherical to cylindrical, how to convert from cylindrical to rectangular, how to go from rectangular to spherical. I mean, it gets to be messy. I give you those equations. You probably ought to go to 11.7 and do a little homework and practice working with them. One of the most famous equations is right here, though. X squared plus y squared plus z squared. I don't know if you can see it, but it's like a 3D Pythagorean theorem here. X squared plus y squared plus z squared is rho squared.
That's a fourth dimension.
No, it's 3 dimensions. It's 3 dimensions. Hey, you know, what is this? X squared plus y squared plus z squared equals 1. Back from our old days of studying stuff. What is that? Sphere. Radius 1. Centered at the origin. Let's convert them into polar coordinate. I mean, Let's convert him to spherical coordinates. And according to spherical coordinates, an x squared plus a y squared plus a z squared is a rho squared. So if I'm going to convert this sucker, I'm going to replace x squared plus y squared plus z squared with rho squared equals 1, baby. Take the square root. Guess what a sphere is in spherical coordinates?
Plus and minus.
Rho equals 1. That's a sphere. Centered at the origin, radius 1. That rho is kind of our new radius. It's our 3D radius. R is our 2D kind of radius. Rho is kind of our 3D radius. That's a sphere. Radius 1. It's beautiful. Beats the hell out of all that crap. I mean, it is kind of an analogy. The circles are so easy in polar coordinates. Well, spheres are so easy in spherical coordinates. All right, so where are we? We finished the chapter in one day. That's awesome. No, not exactly. But we started here today, and I went through 14.4 and 14.5 in like 5 minutes. And my homework reflects that because I assigned 4, 5, 6 problems. 14.6 is good, but it builds to 14.7, and I had to get through here first. And I'm not really through any of this. I'm going to review all this the next few days.
Is it on the homework, the problems for 11.7?
So I've got some homework problems in 11.7 and 14.6, and there's homework problems all through here you should work on. For the quiz Friday, you know, what should I tell you?
14.1 to 14.3.
Stop.
I should just lie to you though, because
It's all inclusive.
yeah, I mean, because you guys, I think you work better if I lied to you. Don't you think?